All right, we are live. Okay, I'll adjust my mic, actually. But in the meantime, hello, my name is Justin Yu. I'm the instructor for today. And I have a tendency of using complex numbers in the worst possible situations, which makes me great for teaching this topic, which is on complex numbers. Is the mic a bit better? Hopefully it is. If not, I guess we can bear with it. All right, cool. So I'm gonna get started. Oh yeah, the TA for today's session is Naveen Mukat. All right, direct all questions you have to him. Are there people in the waiting room? And let me pull up. Oh, admit all. Okay. Enable waiting. Okay. Sorry, I forgot to disable the waiting room once we got ready. So, but let me get the setup and then we'll get started. Oh, and I thought I disabled that too. All right, but anyway, okay, disable. Okay, annotation should be disabled. Okay, let's get started. All right, if I can figure out how to navigate everything. All right, so we're gonna be talking about complex numbers. Fair warning, a tiny bit of trig is going to be useful. A tiny bit of trig is going to be useful, so just hopefully I'll try and go slowly through that. I'm also might go a bit fast because I think I put in way too many problems for this. So if that happens, I apologize, but we will have the video up in due time after it takes its time to polish. And with that in mind, let's get started. All right, we're gonna start with the basic stuff, just boring housekeeping. I'm guessing a lot of you already know these, but it's always nice to just refresh. And we're gonna start with what is called the imaginary unit, I. All right, this is what like complex numbers are all about. All right, and this arose from a simple question: how do you take the square root of -1? All right, you can't. No positive number works because positive number squared is positive. No negative numbers works because negative squares are also positive. And because of this, mathematicians were eventually forced to create entirely new notation, which is what we have here. All right, this is the formal definition. All right, and not only do we have imaginary numbers, which are multiples of I, we also have complex numbers now. All right, which is an entirely new dimension added to just our boring old number line. All right, you can see the definition of the complex number. All right, you can think of it as having two parts: the real part, which is the part that doesn't contain the I, and the imaginary parts, which is the coefficient in front of the I. It turns out that just knowing this is enough to do some basic arithmetic, all of the PEMDAS functions, if you will, because imaginary units obey much of the regular laws. So just as a warm-up, first, we're going to go through these problems. I'm going to have to transition from this slide presentation to the whiteboard. So just bear with me. I'll give you like 30 seconds to write these down. Just think about how you do them, or do them if you know how. All right, let's get started. in a sec if I can try and move some stuff. I'm going to try and move some stuff around. All right, cool. So what do we got to do? Okay, let's take a look at the first question. The first question is finding I to the 57th. And 57 is a very big, very scary number. So let's see if we can break it down to something a bit more simple. So let's start with an easy question. Can everybody tell me what this is equal to? I'm getting a lot of I's, and yes, that's correct. Anything to the first power is just itself. All right, so now we go to I squared. All right, and we all know that's -1. Very good. Next one's a bit trickier. All right, we have I cubed, and seems like you all are already ahead of me, so I think you know what's coming next. I to the 4th. And this is how I'm getting that. All right, I have a negative I squared, but this is just the negative of -1, which is 1. So this is cool because now I have I to the 4th on one side and 1 on the other side. And I know that I can raise 1 to any exponent I want, and I know exactly what it is. So since I want this exponent to be 57, I should raise this entire expression to a quantity that's close to 57, sorry. So can you tell me what exponent I should raise this by? Okay, I'm getting a lot of 14s, and let's see how that would work. All right, we raise both sides to the 14th. What does this become? This becomes I to the 56th. And what does the right side become? 1. So to get from 56 to 57, this was a great thing that we could have done. Kudos to everybody who said 14, because now we just have to multiply by I. And just like that, we've solved our first question. I would like to ask, please submit answers at most once. It doesn't help me if you spam the chat and I can't see everybody's work. So let's get this cleared. And let's start on the next question. All right, and that is evaluating this. All right, so we see different terms. And when we're multiplying things that have different terms, I see distributive property. Other people might know it as FOIL. Either way works perfectly. So let's see what FOIL looks like. So we're going to start by multiplying this, then the inners, then the outers. All right, we're going to do each of these multiplications one at a time. So 2 times 4 is 8. What is 2 times -3i? Getting a -6i? Great. All right, 3i times 4, that's the next one. Plus 12i. Then 3i times -3i. All right, now this is the tricky one. This is the one that gets a lot of people in the first time, because you have to realize that it's +9. Even though we're multiplying a positive and a negative number here, we get I squared, which is -1, right? That substitution is you're always going to want to be thinking of. You never need to have an exponent of I that is bigger than 1. So how do we combine these terms? All right, these look very different. So we're going to have to use our best judgment and combine like terms. So these are real numbers and these are imaginary numbers. So we should combine that to get 17 and combine this to get 6i. Just like that, we have an answer. All right, thank you for the person who was asking how I was doing. I'm doing very fine. So combining of like terms is going to be important. All right, and this is how we do multiplication. Now division is slightly trickier, and that's the subject of the third one. All right, this is 7 plus 24i over 4 plus 3i. And we're going to have to use a special trick that we're going to go more into depth later. For the people asking the person asking about a 9i squared, remember that I squared is -1. So you can actually simplify that even further. All right. Hopefully I explain it well enough in the videos so when that comes up, you will have full access to all of this. All right. I see multiply by the conjugate. I see multiply by 1. Both of those are entirely correct interpretations. All right. And the key thing is to realize we do not want this like imaginary business. We don't want this imaginary business on the bottom. So we want to get rid of that. And it turns out that we can do something called multiplying by the conjugate. Was this 4 that you're worried about? All right, so hopefully you can see where I got this from. This was the conjugate of 4 plus 3i, so instead of a plus, we have a minus. And it would be vice versa. So now we have to multiply the top, but hopefully we have practice with this now, so it's a bit less scary. So the top, we have a 28 minus 21i plus 96i. And then this is going to be minus 72i squared. But since I squared is -1, this is actually a plus 72. And we're going to divide this by, what is this? Now we have to multiply the bottom. All right, this is 16. Next we have minus 12i. Next we have plus 12i. I like where this is going. And finally we have 9. So this cancels out. And when we combine terms exactly like we did before, we have 100 plus 75i over 25. So if we simplify this, what do we get? 4 plus 3i. Right, anybody have any questions? If a lot of people answer, I might go over something again. All right, cool. I'm just gonna keep on going ahead. And this is how we're gonna handle just the basic order of operations. This is the bread and butter of any problem involving complex numbers. So I'm gonna go ahead and if you'll excuse, this is an issue. All right, I'm gonna need to switch back and forth, and that's not exactly the fastest. So let's continue. All right, now we're gonna get, this is the formalization of something that we discussed earlier, the complex conjugates, and this is how we denote it. Oh, what is in the background? I cannot see my face right now, so. Oh, can you? Huh, that was not intentional. I see what happened. All right, is this better? Okay, so this is also how it's denoted. You can choose to do it you do it however you want, just as long as you know what it is. All right, next we have the magnitude of a complex number, right? And it is defined in the following way. All right, so we'll get into the geometric intuition of why this is true later, because the great thing about complex numbers is that they have all this nice geometric intuition, but that's not always necessary. And we're going over the problems where that is not necessary. So let's head on. Hopefully you have these definitions down. We'll go through them. Here are properties. Here are a lot of properties that these satisfy. All right, and these look pretty straightforward. And because they're more or less straightforward, we're not going to really prove them here. But the most important one really is this number 8 on the bottom. All right, just notice that like conjugation works nice with the operations, and taking the magnitude works nice with multiplication or division. And those are going to be intuitions that we are going to continue to use later on. I apologize if I'm covering the bottom. So hopefully we have that in mind. We'll be going over all of this again in a couple problems. But here is our next example. All right, we have all the tools that we need. Yes, pointer, I forgot about that. Excellent idea. All right, so I'll give you 30 seconds. Read this problem, write it down, because I'm going to be switching over to the whiteboard soon. Sorry, I'm not able to go back because I want to make sure that we get through all the problems. I'll be very clear whenever we're using one of the properties. Yes. All right, so hopefully you've had some time to think about this. All right, I'm going to switch over to the whiteboard now, and I will rewrite the equation. So z is equal to z plus n, or z over z plus n is equal to 4i. So now, what do we know about z? That's the first question. All right, and we know that z is a complex number. It tells us that. So that means that we can write it as a plus bi. And the problem actually tells us something more. It tells us the value of one of these numbers, a or b. Now, do you all remember the definition of an imaginary part? I imagine some of you don't, but it's just the part in front of the I. You can think of this as the real part and this as the imaginary part. So we know that b is equal to 164, so we can actually write it like this. B is 164. I saw a couple of answers saying that z was equal to n plus 164 high. However, this is dangerous because n is defined entirely differently in this problem. And we don't know that there is a correlation yet. So we're going to have to stick with a for now. So what do we have? A plus 164i over a plus n. 164i. And this is equal to 4i. The problem actually does not say that the real part is n. It says there is a positive integer n, such that this equation works. And that's going to be a distinction. You would have been able to certainly been able to see that if you had access to the problem for a longer period of time. Yes, thank you, Naveen. And I do not believe your equations would have worked out if you actually did substitute n. So that would be a cue that something's wrong. So we have to solve this equation now. So we know that fractions always make things worse, so we're going to try and multiply them out. That's easy here. It's going to be equal to 4 times 164. That's going to be 676. Is this correct? No, 656. Thank you. But it's actually a negative 60. It's actually a negative 656 because we have this I squared. All right, note how I'm keeping my work organized. I'm separating the real parts and the imaginary parts. So let's take a look at these pairs that I'm outlining. Whenever you have an equation for a complex number and you write it like this, you actually have two equations that are nicely packed into one. This is because if these two complex numbers are equal, the real parts have to be equal and the imaginary parts have to be equal. So already, right off the bats, we know that a is equal to negative 656. That's great, because we also know that 164 is equal to 4 times a plus n, which we could simplify to 4 to 1 just by dividing by 4. So now, can you all fill in the rest of the gaps for me? Tell me what the value of n is. All right, 697 seems to be the most common answer, and that is correct. Why is a equal to negative 656? Great question. The reason is because When we multiplied these two terms, that worked out to negative 656 because of this I squared. And then when we compared the real parts of both sides, we knew they had to be equal. And it just happened to be really nice for us because this is the only real part and this is the only real part on each side. Great, so hopefully you can see how just a little computation and a bit of algebra can get you a long way. This was an Amy problem, actually. So, but let's not get content quite yet. All right, and let me go back here. This was the 2009. Yes, thank you for the recurring strategy. That's what I was trying to say, except much nicer. All right, so now we have an ARML problem, all right, from competition. This is a bit similar. This uses that magnitude notation that we introduced earlier, so I'll go over that, but just take a few seconds to get this copied down so you can work on it. I will try and rewrite the problem when I switch to the whiteboard. All right, I'm hoping you all have had enough time. Let me give you 5 more seconds. And let's get cracking. Let's also be clean and clear at work. So we're given this sort of multi-layered equation. And if calling z a complex number was an I wouldn't tip you off, this I over here most certainly would. That first z looks like a 2. Sorry, that's going to happen. I'll try and make it as clear as possible. All right, so how should we go about doing this? All right, what do we know about, like, what's the method that we've used? All right, I'm getting a couple suggestions. Anybody else have one? All right, I see one solution that you're actually going to have to wait on. All right, the most frequent one I'm seeing is using a plus bi. You're going to have to wait a bit for the perpendicular bisectors, but we will get to that, or at least I will try to. All right, I just want to show that bashing is still powerful. So let's like plug this in to everything that we know. And notice how I'm continuing to keep my work organized, grouping the real parts and the imaginary parts. So does anybody remember the formula for the magnitude of a plus bi? All right, great. It is the square root of a squared plus b squared. You cannot forget that square roots. Yes, Pythagorean theorem is the motivation. So let's see if we can do that here. So the magnitude of this is the square root plus b squared. Continuing. And continuing. All right, so now what should we do with this equation now? Notice how we've like completely gotten rid of any notion of complex numbers. And what should we do with this to make the equation nicer? All right, get rid of the square roots or square everything. We do both at the same time. Nice. And I'm also going to go ahead and expand. So a squared minus 2a plus 1 plus b squared is equal to a squared plus 6a plus 9 plus b squared. And that's also equal to a squared plus b squared plus 2b plus 1. All right, so, right, I like the idea that I see we can get rid of the a squared plus b squareds from everything. All right, a squared. All right, and keep in mind, this is a negative 2a. All right, so now what we want to do is we want to take these equations 2 at a time. And the reason we do 2 at a time is because then we can use solving methods a lot easier. So let's take the first 2. And this is nice because this is a one variable equation. Can anybody who hasn't figured it out already tell me what a is equal to? Okay, I'm getting a lot of negative ones. And that is correct. Yes, a is equal to -1. So now we can use this information to solve for b. And what we're going to do is we're going to plug it into either one. Let's say we get 3 is equal to 3 is equal to 2b plus 1. All right, and people already finished the next step for me. B is equal to 1. So what is our final answer? All right, the most frequent one I get is -1 plus I. And yes, that is correct. Because remember the problem statement, the answer was a complex number. And it turns out there's only one that works. And we found its real part here and its imaginary part here. Great. See, just simple algebra, canceling out common terms from both sides, squaring things that we don't like, all the good stuff. All right, no advanced information was needed. The question did ask for all values of z, but we only found one. So there only is one. It's sort of a trick question, if you will. So this is meant to be the general overview of the complex numbers. And it's time that we get into more specialized topics. All right, and these specialized topics are going to be polynomials. All right, remember, complex numbers were originally created to solve polynomials like x squared plus 1 equals 0, because how do you do that without I? And it turns out that complex numbers are really, really nice because actually every root of a polynomial can be written as a complex number. This is known as the fundamental theorem of algebra. All right, basically, a degree n polynomial has n different roots. All right, and they are all complex numbers. When we say n different groups, we're counting repeated ones as difference for reference. So for example, the equation x minus 1 squared has 2 roots. It only has one value, which is 1, but the multiplicity, or the number of times it appears, is twice. Right? Equally important is lemma 2.2, which is down here. And that's how you're going to want to think about complex numbers. And that complex numbers actually come in pairs. All right? If a plus bi is a root of a polynomial, then a minus bi is also a root of polynomial. All right? And there's an important caveat, is that lemma 2.2 actually only applies to polynomials with real coefficients. So if the coefficients of a polynomial was like 1 plus I, this wouldn't work. All right, but the vast majority of like every polynomial you will ever see in a competition will be real, so you can apply this lemma. All right, and now let's take a look at an application problem, this time from Purple Comet. I think the intended solution was for people to bash this out on calculator. But we're not going to do that because we are superior. So we are going to use our knowledge of turning things into equations and complex numbers to solve this. All right, give you 30 more seconds to get this problem copied down. Note all the important parts. Then I will switch to the whiteboard. All right, I hope that was enough time. Let's get started. So what is the first thing that you should do whenever you see graphs or parabolas? Okay, after you read the question, because that is the 0th thing that you should do. Solve for intersection, substitution, isolate the y. None of this helps me understand the problem any better. This is just bashing. Let me write down the... I'm getting a lot of what I was hoping for, and that is to graph the problem, yes. Right, because like when we graph the problem, we are able to... Then x is equal to y squared plus k. The original problem said this k was an m over n, but that's what it really asked for. So the y equals 4x squared, that's a straightforward parabola. It's going to be long and narrow, have curving sides like this. All right, so then when we draw the x equals y squared plus k, it might look something like that. So you can see this really, really small distance is the k value. And this is the intersection. So, all right, so now that we have an idea of what's happening here, let's go to an earlier thing in substitutes. Should we plug in a value for, should we plug in y as a function of x or x as a function of y? Which one do you guys like better? Plugging in x as y, I'm actually getting a lot of different answers. I'm going to go ahead and stick with the more direct one. This is a direct equality, so it's easier to work with. So now I get x is equal to 16x to the 4th plus k. So if I move everything, all right, does anybody know the quartic formula off the top of their head? Because it looks like we're going to need to solve a quartic. All right, and while I'm at it, I'm going to go ahead and write the polynomial like this. All right, and this makes the polynomial monic. Monic means its coefficient is 1, which is usually how you see most quadratics. All right, so we're going to need to be a bit smart because the answer to this question should be nice. Like we know that the answer should be a fraction, which means that it's possible to factor this. Right? How do we usually factor like cubics or quartics? Like what, is there a tool that helps us with this? I'm seeing grouping, Pascal's triangle. Those are all great techniques, but none of them will work here. All right, if any of you have heard of the rational root theorem before, it doesn't matter in this case because you can't use it here. So we're stuck. All right, we have this equation and like we just don't have any information because how can we guess roots if we don't know what k is? Well, it turns out we do have information, and that information is right here in this picture. How many solutions are there supposed to be? I see, yeah, one intersection. Right, you all see there's one intersection. So how many real solutions? How many real solutions are there to this? Getting a lot of ones. Right, it seems like 1 is the dominant. So if there's one real solution, then what do the other 3 solutions have to be? They have to be complex, yeah, or imaginary, whatever you like. But there is a slight problem with that. Does anybody remember what lemma 2.2 says? For those of you who don't, they have to come in pairs, which means the number of complex roots has to be even. All right, 3 is not an even number. How do we solve this? All right, how can we have like 1 real roots and 2 complex roots or 4 complex roots? And I'm seeing the solution from a lot of people, and it's that you make it a double root. All right, remember, double roots are still 1 value, it just counts multiple times. But we also have to check that maybe it's quadruple roots. Do you guys think that this is that we can factor this in the form x minus a to the 4th? Like maybe it could be a quadruple root. Maybe there are 0 complex roots. We don't know. Does this work? It does not. So yeah, we're gonna have to stick back to the game plan. So I'm gonna write the complex roots as a plus bi, a minus bi, c, and c. And because we're starting to run out of time, I might have to go a bit fast. So I'm sorry if it's a bit much. So now we know that this is factored as x minus c squared times x minus a minus bi times x minus a plus bi. All right, so now we know this looks like that. And we'd want to be able to solve for a, b, and c. So what we should do is we should expand. All right, let's see if we can compare coefficients. But before we do that, here's a trick. All right, and this trick is sort of related to Vieta's formulas. And basically the idea, you would have gotten the exact same thing if you expanded this out. All right, we're gonna try and compare the coefficients of x cubed of these two. What is the coefficient of x cubed, by the way? All right, 0, great. And it turns out that the coefficient of x cubed is also -1 times the sum of these roots. So if we add up these all up together, we get 2a plus 2c is equal to 0. So that means that a is equal to -c, and we can actually get rid of this variable right now. So now we have to expand this, and this is what it's going to look like. I'm going to go fast. All right, minus 2a plus, and this is 2ax. All right, so now we're going to need coefficients for the x squared and the x terms, because those are the remaining ones that we have information for. So the coefficient of x squared, you can do this by FOIL. All right, a squared times x squared, 2ax times -2ax, x times a squared plus b squared. So it comes out to this. All right, and then the x term, the x coefficient comes out to this. A squared minus 2ax, 2ax, a squared plus b squared. So that's actually going to factor pretty nicely into 2ab squared. And then we know the constant term is a squared times a squared plus b squared. And we're going to have to plug this in at the end to find our value of k. So I hope you all don't mind if I clear away this business now that we found everything we need for our necessary equations. All right, so we need to compare the two x squared coefficients. So we know that b squared is 2a squared. And we also know that 2ab squared is -1/16. So I'm going to plug in for b squared right here. So I get 4a cubed is equal to -1/16. So now can anybody tell me what a is equal to? I got -1/4? Yep, that's exactly what it is. We just solved this equation by dividing by 4, taking the cube root. And we can plug it in. So we know that a squared is 1/16. So b squared, which is 2a squared, is 1/8. So I'm going to reserve the space in the middle for our final. K over 16 is equal to this, which is a squared times a squared plus b squared. or that should be a 1/8. And when you simplify all of this, you get that k is equal to 3/16. A nice number. And this is our answer. So hopefully you see that the main step was figuring out the factored form. Right, b squared is equal to 2a squared because this is the x squared coefficient and it's equal to 0. Yeah, I suppose the answer is 19 if you go technically, but we found the value of k and that's all we care about. But hopefully you realize the main step was noticing that this tangency condition, we could figure out the factored form of this. And once we had the factored form, we just had some equations that we could solve. All right, hopefully everybody's good with that. All right, we're gonna continue moving on. I hope we might run a few minutes late. I hope some of you will be able to stay for the rest of it, but all of it will be uploaded. All right, we're gonna get to the next part. All right, so now we introduce some these are like the common results involving complex numbers. All right, so first we have this theorem, and I'm gonna skip the proof because it requires knowledge of trigonometric identities, which I'm not entirely sure that all of you have. But if you do want to do it yourself, you can do it by induction. All right, the proof will also be in the handouts. All right, and we'll see later that this form of representing complex numbers is very nice because it also helps us see the solution to this fundamental equation, x to the n minus 1 equals 0. Oh, yes. Thank you for noticing the typo, Brian. There is a typo here. This is supposed to be 2k pi I over n. All right, that will be fixed, but just remember that there should be an I up here. So it turns out that these are the roots of unity. And basically what you do is if you plug in each of these numbers to this formula right here, you get something like cosine of 2 pi, which is 1, plus I sine of 2 pi, which is 0, or 1. So then this number raised to the nth power is equal to 1. All right, and I'm going a bit fast, so let's take a look at this sample problem, which uses these roots of unity. All right, and this is gonna be like completely sticking to the definition. After we get this, we're gonna get to the really good stuff. All right, I'm gonna go ahead and share the whiteboard. So here are the necessary conditions. All right, z to the 13th equals w. W to the 11th equals z. Imaginary part of z, which is sometimes written like this, equals sine of m pi over n. Find n. And this is z to the 13th, actually. Okay, so first off, this condition is entirely dependent on z. So we want to combine these two to get an equation that only involves z. So what does this look like? The equation that only involves z. Cool. Z to the 143 is equal to z. And we know that, like, we're pretty sure that z is not gonna be 0. Like, I'm not sure if that's given by the problem statement, but we can assume that safely enough, so we can actually divide by z. It gets z to the 142 minus 1 equals 0. Yeah, hopefully this looks familiar. This is exactly the roots of unity equation. So as a reminder of what the definition is, z is going to be equal to cosine of m pi over 2 m pi over 140 plus I sine of 2 m pi over 142. This is just the definition of the roots of unity. All right, and we'll see like where I get these expressions from later. Just need to get through this. All right, so what is the imaginary part of z based off this expression? second part, right? And that is the sine parts. And we can divide out this 2. So if we compare these two, what is n? N is 71. We actually don't know anything about m. M could be 1, m could be 2, m could be 50. Each of those are actually equally valid. So yeah, we say that like it's going to have to be 71. But since this is an Amy, we cannot forget our first digits. So that's actually the answer. This seemed a bit hard. Don't worry. This will all be in the handout. It will all be explained very clearly. So let's get going to the next one. All right. Okay. So before we do that, let's start by introducing some new notation. All right. And let's actually introduce an entirely new picture. What picture have I just drawn? A graph. I'm seeing a lot of coordinate planes. And yes, that's exactly what this is. However, we can also use it as a complex plane, where the x-axis is like the real axis. The y-axis is the y-axis. So this is an example of like where the point 3 plus 2i. 3 to the left, 2 up. All right. And it turns out that oftentimes it's more convenient to represent complex numbers in this form. Right? It has a radius and an angle. All right, so now we can express this in a bunch of different ways. Yes, this is the angle made between this line and the x-axis. So first off, we can find the x and y coordinates using trig. This is r cosine theta. This is r sine theta. All right, so let's call this complex number z. Z is equal to r cosine theta. This is the real part. I r sine theta. This is the imaginary part. We have a couple ways of abbreviating this. All right, this cis of theta is cosine theta plus I sine theta. And you might recognize that expression from the roots of unity that we just went over. And we can also represent it as r times e to the I theta. All right, and representing this like an exponential is actually really cool because it suggests something very powerful about this notation. We are assuming the dotted line is perpendicular to the x-axis. So let's say we were trying to multiply two complex numbers z and w. And z was equal to r1 times e to the I theta 1. And w was equal to r2 times e to the theta I theta 2. All right, just different representations. All right, now what happens when we multiply zw? Well, using our exponent properties, we get this. And this is cool because, let me draw it here. Let's say that this was equal to w, and that was theta 2. What we've just done is we just added these angles and multiplied their magnitudes. So we get this is zw. And this is part of why complex numbers are so good, is because they actually make rotations work really nicely. All because of this. So just remember, if you remember anything from this, it's that when you multiply two complex numbers, you multiply the radii, you add the angles. All right. Let's connect. We can also connect this back to some stuff we discussed earlier. This is, for example, let's say this is a plus bi. Then the conjugate looks like this. All right, you can think of it reflecting across the x-axis. The magnitude is just the length of this. All right, because of Pythagorean theorem, we know that this is square root of a squared plus b squared. And now you see where that formula comes from. Finally, another important thing is addition. Let's add 2 plus I and 3 plus 2i. So those numbers can be represented, actually, let me make this 2 plus 3i. It'll be easier to draw. That's a 2, and this is a 3. All right, so you're going to notice I'm going to be drawing these with arrows. That's because complex addition looks really nice. Basically, we can take this line and translate it so it looks like a parallelogram. And it turns out that this is 4 plus 4i, or it would be if it was drawn to scale. So this is how we can think about it. All right, we can just think about it. Somebody mentioned vectors earlier. That's exactly what it is. Sort of this translational. And we'll go over all this again in the next couple problems. And then by that time, I think I'll have gone a bit over. So let's get started with the first problem. And I'm actually going to just show this for you right now. Go back to the back here, or back to the whiteboard, because you've already seen this before. This is that Armel problem that we did. Right? Maybe you remember that we did it. Yeah, we did it like z is equal to a plus bi. Let's think, how does this work geometrically? All right, so what do magnitudes mean? Magnitudes mean distance. All right, and it turns out that when we have something like a minus b, it's the distance between a and b. So let's try and see what that looks like. All right, we have z minus 1. So I don't know where z is, but we're looking for the distance between the point z and the point 1. So this is the point 1. If we continue this logic, this is the point -3. It's over here. And this is the point -i. We're subtracting -i. And let's say like here. So let's say this is z, this is 1, -3, and this is -i. So now the key is that each of these distances are exactly the same. Why are they the same? It's because that's what the condition gives us. Right? These distances are all equal. But hopefully this reminds you of something that occurs in geometry. And that is the Circum Circle, or the Circumcenter. We could draw a circle like this, centered at z with fixed radius. And do any geometry whizzes here, can you tell me how we define the circumcenter? Right, I see that we use the perpendicular bisectors. So we're going to need to pick 2 perpendicular bisectors that are easy to use. I see this horizontal line. So I want to use that because that's just this. All right, the equation of this, what's this midpoint right here? That's -1. X is equal to -1 is like the equation. The other one that I want to use is between this, because this has slope 1, and slope 1 is good. So if I draw it, I notice that it passes through the origin. So can anybody tell me what the equation of this line is? And again, I apologize if I'm losing some of you. I'm trying to get through this quickly so that I can move on to the last problem, which is really something and a really great example of like why bashing everything with algebra is not always the move. And I get y is equal to -x as the other one. So we want the intersection of these 2 lines. And they intersect at -1, 1. And of course, because the x is the real part, the x-axis, the y is the imaginary axis, we once again arrive at -1 plus I. All right, now let me take a survey. Which way did you prefer? The algebraic way, where we just bashed and squared, or the geometric way, where we just drew a nice picture? Oh, I like what I'm seeing. I'm getting a really nice mix of both. All right, you can always usually pick which way you want. Algebra is a lot more simple. Geometric is hard to see, which is why it's especially important to just have in the back of your mind memories of what each of these represents. But there are some questions where this just doesn't work. I'm going to show you one of them. All right, I will give you a minute to take a look at it. And then we will go. This is a problem that I actually solved in a competition last Saturday. And I thought it was just a perfect example for this, so I really wanted to include it. Farmal stands for fake armal. So yeah, hopefully. All right, this is, again, like a lot harder. It's possibly beyond the scope of this class. So if you need to leave at the end of the hour, go ahead, but I hope you will stay because this is a cool problem. And it's nice in geometry. All right, there's surprisingly little algebra. Another thing I'd be interested is if one of you tried and do the algebra way. All right, x is equal to a plus bi, y is equal to c plus di. This is what I tried at first when I saw this for the first time. But you have my assurance that this doesn't really work that well. You have a lot of squared expressions, lots of like some expressions that are even cubed, and you're solving for 3 variables, and it just doesn't really pan out that well. Hopefully you've had enough time to admire the problem. I will copy down the equation. And let's get to it. So the first thing that I do when I look at this problem is I see if there are any like interesting structures, like symmetries that I can take care of to make the work easier. This is always something that you should do. So I see somebody said 5y. I'm assuming that means like there's a 5y here and a 5y there. Fortunately, one of them is within bars. So it's not really going to help us that much. We can't really cancel out anything, which is a pity. All right, there are interesting expressions that take great advantage of the principles that we've already discussed. All right, so casework with the absolute value. The absolute value is always going to be positive, and it's all over the place. So, ooh, I see somebody say the imaginary parts of 6x and 5y cancel. Now, why is that? I think about why must the imaginary parts cancel? Which means that this is a real number. Nice. So these absolute values, these magnitudes, these are real numbers, right? They don't have i's in them. So this is real plus real, so the entire thing is real. So I'm going to put that here and underline it a bunch because it's super important. So now we get to this expression. All right, so x over y is imaginary, and this is also real. All right, why is this? Because if this is a real, then like if we divide by I, remember multiplication and division are like the same thing as adding angles. So let's say we had this number x over y, and we multiplied by I. That's actually the same thing as rotating by 90 degrees, because we're multiplying by this complex number. So we expect x over y to be like somewhere here. But if multiplication is adding angles, division is subtracting angles. So if division is subtracting angles and x over y is a 90-degree angle, what is the angle between these two? Between x and between y. And this is the real crux of the problem, because the final step from here is so nice. The angle between these, it's not 0. All right, it appears I lost basically everybody. That's fantastic. All right, I'm getting a lot of different answers. Yeah. So I'm going to go ahead and spoil it. The angle measure between these is 90. So to see why that's true, let me draw you a picture. Just hopefully convince you that this is correct. Let's say this is y and this is x. This is y and this is x. All right, so I intend for this angle to be a 90-degree angle. So when I divide x by y, I'm subtracting this angle, which is the same as moving it over here. So some line like this is going to look like x over y. All right. You see that I'm just like subtracting the angles because I'm dividing. But because I multiply this by 90 degrees, it goes all the way over here. So this is x over y times I. All right, hopefully more of you are convinced that this is the correct interpretation, that x and y are 90 degrees apart. So let me clear up some space. And let's see what happens when we work with this information. So let's say this is y, and this is x. What do we know about 6y plus 5x again? Or 6x plus 5y? It's real. So you remember how I drew that addition, with the arrows on the complex plane? We're going to be doing the same thing here. We're going to be making this picture. So I'm going to scale out. And I'm going to label this as 5y, and I'm going to label this as 6x. Remember, they still make that 90-degree angle with each other. And it's going to land right here. What shape have we just created? Everybody sees the right triangle. And what do right triangles make us think of? Like, what is the first thing any of us learn when it comes to right triangles? Okay, great. Pythagorean theorem. Maybe we can apply that. How can we express the magnitude of this? All right, I see absolute value. Can you be a bit more specific? All right, because this is 5y, the magnitude of it is just the magnitude of 5y. Because this represents 6x, what is the length of this side? So what this triangle looks like. All right, and then we just take the magnitude. And now here's the cool part. What is the length of the hypotenuse? Now I want you to think hard about this, because length of the hypotenuse. It's z. Yeah, but how can we express that in a better way? See, a couple people see it. The best way is like that. Because it turns out like this is like intuitive, like if you scale it, you can factor out the 6 and you can factor out this 5. You factor out this 5. So now we have an equation in terms of magnitude of x and magnitude of y. All right, so we want Pythag. Let's get some Pythag. So this squared plus that squared is the other squared. 36 times the magnitude of x squared plus 25 times the magnitude of y squared is equal to, we're going to have to square this, so. And is everybody okay with how I move these 5s outside? All right, so now we have to solve this. Well, I see something that we can do. We can cancel out these 25y squareds. And we can get rid of this, and this becomes an 11. So 11x squared is going to be equal to 50. All right, and then we divide by, oh, and this squared actually should be outside. That's a big difference. Do we divide by 11x, so we get magnitude of x. Let me write that better. And now we have this. This is a nice equation. And now here's the final like magic part. We're done. We are actually so done. We can just plug these in directly into one of these equations and we're golden. But it's really hard to see which of these equations it is. So I want you to try and figure that out. Because this next step is maybe not obvious. To which of these expressions for z do we plug this in? All right, the last one. All right, why can't we plug it into the last one? All right, these do not have magnitude bars, and these have magnitude bars. Here's the trick. I have not seen the answer that I was looking for. What we can do is we can take the magnitude of this. So this is going to rely on some of those properties that we discussed a while back. Okay, so what is the absolute value of what is the magnitude of a real number? It's just a real number. All right, and we can break this up into magnitude of I times the magnitude of x over the magnitude of I. So can everybody tell me, what is the magnitude of I? The distance from I to the origin. So this goes away. So now we have this equation. Can anybody tell me what the answer is? (50/11). Bingo. That's it. We're done. That was the problem. Okay, this was a monster of a problem. So I'm going to summarize what we did again. First, we used this equation to realize that the entire expression is just dealing with real numbers. And this was powerful because we could use this in a couple ways. First, because this expression is real, we can deduce that x and y are 90 degrees apart on the complex plane. Secondly, because this expression is real, we can see that if we add it graphically, we create this right triangle. Finally, we know what the sides of the right triangle are, so we can set up an equation purely in terms of these basic magnitudes. And then once we did that, we just plugged them in to here, and we got the answer. All right, so hopefully all of you found something that was interesting about this. The handouts will be coming out in a few days. Please give us patience. It takes us time to polish them and make sure that they don't have mistakes. Yeah, please answer Naveen's poll. This is a hard problem. But think about it. We did not have to write down a single equation for A and B. Right. Sorry, you're gonna have to. Okay, so I'm gonna stop sharing and I'm gonna stop recording. Uh-oh. Stop recording.